Welcome, everyone. Ready to dive deep into some aviation physics?
I'm ready. Let's do it.
We're going to be exploring some fascinating excerpts from an Aviation Maintenance Technician General Handbook.
Yeah, should be interesting.
Think of this deep dive like a backstage pass to understanding how airplanes actually work.
Like getting under the hood and really seeing what makes them tick.
Exactly. So let's start with something we all know. Matter.
Seems simple enough, right?
It is, but it's also the foundation of everything, even those giant jets we see flying around.
Right. And the handbook reminds us that matter can't be created or destroyed, just changed.
Yeah, like when an airplane burns fuel.
Exactly. Transforms that matter into energy and exhaust.
Okay, so we know an airplane is matter, but
Mm-hmm.
what about, say, an astronaut in space?
Ah, interesting.
They seem weightless.
Right.
Does that mean they no longer have mass?
Good question. They still have mass, which is the amount of stuff in an object, but weight is actually gravity's pull on that mass.
Hmm.
In orbit, they're in constant free fall, so it feels like they're weightless, even though they're still made of matter.
So that's why they float around.
Exactly. It's all about the interplay between mass and gravity.
That makes a lot of sense. I always wondered about that.
Yeah, it's a common misconception.
So gravity is key, but there's more to matter than just that, right? The handbook mentions density.
Density, yep.
Why is that so important when we talk about planes?
Well, density is all about how tightly packed the matter is in a given space.
Okay,
And it affects everything from the materials we use to build a plane to how it reacts to the air around it.
I see.
Think about how temperature and pressure affect density, for instance.
Okay.
That's why hot air balloons float. The hot air inside is less dense than the cooler air outside.
Oh, never thought about it like that.
Yeah. Pretty cool, huh?
It's like how a boat floats, right?
Exactly. It displaces a volume of water equal to its own weight because it's less dense.
Speaking of density, I think there was something in the handbook about using a hydrometer to check the charge of an aircraft battery.
Oh, yeah, that's a great example of how a simple physics concept has practical applications.
Wow.
The density of the battery fluid, also called the electrolyte, can tell you how much charge the battery has left.
Really?
Yep. It's like magic, but it's just physics at work.
So you're telling me I could impress my mechanic friends with some physics trivia.
Absolutely.
All right, I'm adding that to my list.
Huh. Good.
Now, we've talked about matter, but to get a plane off the ground, we need energy.
Right.
And the handbook dives into different types, starting with potential energy.
Potential energy, the energy of position or state,
Exactly, like a coiled spring or a rock on a cliff.
or a plane being raised for maintenance.
Yeah, that height gives it a lot of potential energy.
A lot. The handbook says a Boeing 747 just raised 4 feet has almost 2 million foot-pounds of potential energy.
Wow, that's a lot.
It is. And the handbook also mentions the potential energy stored in a full tank of aviation gas. That's chemical potential energy.
So that's the energy stored in the bonds of the molecules, just waiting to be released.
Exactly, ready to be unleashed through combustion.
And when that energy is released, things start moving. That brings us to kinetic energy.
Ah, kinetic energy, the energy of motion.
A plane speeding down the runway, the whirling blades of a turbofan engine.
All kinetic energy in action, and the faster an object moves, the more kinetic energy it has.
So we've got all this energy,
Yep.
but how do we use it to make things happen, to actually make a plane fly?
Well, that's where the concepts of force, work, power, and torque come in.
Let's break those down.
All right, let's start with force. Force is a push or a pull that can change an object's motion.
Makes sense.
The handbook gives a great example. The GE90-115 turbofan engine, which can produce 115,000 pounds of thrust.
Wow, that's more than 50 tons.
Yeah, it's a lot of force.
And when that force is applied over a distance, we get work.
You got it. Think of a tow tractor pushing a 737 into a hangar, that's work being done, or jacking up an Airbus A320 for maintenance.
Yeah, I can see how those would require some serious force.
Definitely.
So work is force in action, but what about power? Isn't that how quickly work gets done?
Exactly. And this is where the handbook has a fun little fact.
Mm-hmm.
You know how we measure power in horsepower?
Yeah, that's a pretty common term, even outside of aviation.
Well, the term actually comes from comparing the output of steam engines to the work that a horse could do. It's a fascinating little origin story.
I never knew that. So horsepower is literally about comparing engines to horses.
Pretty much, and the handbook gives a good example to illustrate power. Lifting a massive GE90 engine for installation takes a surprising amount of horsepower.
It's amazing how much power is involved in aviation.
Definitely, and we haven't even talked about torque yet.
That's right, torque. I know it has something to do with rotation, but it's always been a bit of a mystery to me.
Torque is basically a twisting force that causes rotation, and the handbook makes a point of saying that it's a force acting along a distance, not through it like with work.
I see the distinction.
Think of it like tightening a bolt with a wrench.
Okay.
The length of the wrench acts as a lever arm, and the force you apply creates torque, causing the bolt to turn.
So torque is like a lever in action creating a twisting force.
Exactly.
Mhm.
And it's essential in both piston and turbine engines.
Really?
Yep. The handbook has some great visuals explaining how torque is generated and used in these engines.
It's amazing to see how these physics concepts are at the heart of everything in aviation.
It really is. It's all connected.
We've gone from the building blocks of matter to understanding how forces and energy create motion.
And this is just the beginning. Next, we'll explore how these concepts translate into the actual mechanisms that make flight possible.
I can't wait. So we ended on torque last time.
We did?
I have a feeling we're just scratching the surface of how all these concepts actually, work together to make a plane fly.
Yeah, there are a lot of amazing mechanisms at play.
Like what?
Well, let's take a closer look at simple machines, for instance.
Levers, pulleys, gears.
Exactly.
This stuff we all learned about in school, but never really connected to airplanes.
Yeah, but they're everywhere in aviation.
Really?
Oh, yeah, big time.
Hmm.
Simple machines are all about making work easier,
Easier how?
Like they might change the direction of a force or multiply a force or even multiply speed. It all depends on the design.
So give me an
That's what
example.
I said. Oh.
Where would I find a simple machine on an airplane?
Well, take a look at the landing gear.
Okay.
The mechanism that retracts and extends the wheels,
Yeah.
that uses a system of levers and hydraulics. It's a beautiful example of multiplying force to move something really heavy.
I see. So it's not just brute strength moving those wheels.
Nope, it's clever engineering using simple machines.
That's really cool. I'm starting to see how these things are connected.
Yeah, it's all related.
The handbook mentioned something called mechanical advantage.
Uh-huh.
Is that related to simple machines?
It is. Mechanical advantage is all about how much a simple machine multiplies the force you put into it.
Okay.
So if you have a mechanical advantage of 2, you only need to apply half the force to move the load.
Wow, that's incredibly helpful.
Yeah, especially when you're dealing with those massive weights involved in aviation.
Right. And speaking of which, the handbook goes into levers,
Levers, yeah.
classifying them into 3 different types.
First class, second class, and third class.
Are all of those found on airplanes?
Definitely. Yeah.
Cool. Give me an example of a first-class lever.
Okay, well, a great example is a crowbar.
A crowbar.
Yeah, used all the time in maintenance.
Wow, okay.
You apply force on one end, the fulcrum is in the middle, and the load, whatever you're trying to pry, is on the other end.
Makes sense.
And the handbook mentions that a plane's balance can also be thought of as a first-class lever.
Really?
Yeah, with the center of lift acting as the fulcrum.
The weight of the plane is like the effort and resistance.
Exactly, determining the plane's pitch.
That's fascinating.
And it is. It's physics in action, even in something as seemingly simple as a plane's balance.
Okay, what about the other types of levers, second and third class? Are those used in airplanes?
They are, although not as commonly as first-class levers.
Okay.
Second-class levers, like a wheelbarrow, are really good at multiplying force. Think about certain types of flaps on a wing.
Flaps, those things that extend down during takeoff and landing.
Yeah, those can function as second-class levers with the hinge acting as the fulcrum.
I see.
They help increase lift.
So even the way flaps work is based on physics.
It all comes back to physics.
What about third-class levers?
Those are the ones that prioritize speed over force.
So those are all about precise control.
Exactly. Think of the control stick in the cockpit.
The one the pilot uses to steer.
Yes. That's a third-class lever, allowing the pilot to make small movements that translate into larger movements of the control surfaces.
So that's how pilots can maneuver such a massive object with just subtle control inputs.
Exactly. Simple machines multiplying force and speed to achieve amazing feats of engineering.
Wow, this is blowing my mind.
Just wait, there's more. Next up, pulleys.
Pulleys, okay.
They're fantastic for changing the direction of force.
Like those old cartoons where they use a rope and pulley to lift something heavy up to a high window.
Exactly. And they can also provide mechanical advantage, especially when you combine them in a block and tackle system.
So you could use that to lift heavy components during maintenance.
Yep. The handbook gives some really impressive examples of how much force can be multiplied using these systems.
It's amazing how something so simple can be so powerful.
Simplicity is often the key to elegant solutions.
We've covered levers and pulleys. What about gears?
Ah, gears. They're like rotating levers, transmitting torque and changing the speed or direction of rotation.
Right, I remember gears from those old clocks and watches.
They're still used in those, but they're also essential in both piston and turbine engines.
Oh, really? Yeah, I didn't know that.
Yeah. Oh, yeah. Different types of gears, spur gears, planetary gears, worm gears, each with its own job to do.
Planetary gears, those always sounded kind of intimidating to me.
They are fascinating. Planetary gear systems are like little mechanical masterpieces.
Oh.
Yeah, consist of a central sun gear surrounded by planet gears, all enclosed in a ring gear.
It's like a mini solar system inside an engine.
I like that analogy. And this intricate arrangement allows for a lot of gear reduction in a small space, which is crucial for aircraft design.
So it's like packing a lot of power into a compact package.
Exactly. And that's essential for things like propeller systems, where you need to translate high engine speeds into the slower, more powerful rotation of the propeller.
That's really clever.
It is. It's incredible how much engineering goes into something we often take for granted.
This deep dive is really opening my eyes to the intricate world of aviation mechanics.
It's amazing what you discover when you start looking closer.
Speaking of looking closer, the handbook mentions something called stress and strain.
Stress and strain, yeah.
So this is about making sure the airplane can handle the forces it experiences during flight.
Exactly. Stress is created whenever a force is applied to a material.
Okay.
Imagine you're bending a metal rod. You're putting stress on it.
Right, like putting pressure on it.
Yes, and that stress acts on every part of an airplane.
The wings, the body, everything.
Everything. And there are different types of stress: tension, compression, torsion, bending, and shear.
Wow. So many ways to stress something out.
And understanding how materials react to stress is key for building a safe and reliable aircraft.
Makes sense. You wouldn't want a wing snapping off mid-flight.
Exactly. That's where strain comes in.
Strain, right. That's how much a material deforms under stress.
You got it. Like how much that metal rod bends when you apply force to it.
So it's like a measure of how much a part is being pushed to its limits.
Exactly. And the handbook gives a great example of how strain can be used for precise measurement.
Yeah.
They talk about a deflecting beam torque wrench, which uses the strain on the wrench beam to very accurately measure torque.
So even the tools mechanics use rely on these physics principles.
It's all connected, from the smallest wrench to the largest jet engine.
Okay, so we've covered matter, energy, simple machines, stress, and strain. I feel like we're building up to something big here.
We are. We've laid the groundwork, and now we're finally ready to explore the forces that make it possible for these huge machines to defy gravity and soar through the air.
All right, let's do it. Bring on the physics of flight. All right, so last we left off, we were talking about stress and strain.
Right, the hitting forces acting on an airplane's structure.
Pretty mind-blowing stuff, but I think we're all ready for the main event. How does a plane actually fly?
The million-dollar question.
What's the secret sauce?
Well, before we get to lift, the handbook actually takes us on a little detour into another fascinating aspect of physics: heat.
Heat. I thought we were done with that back in thermodynamics class.
Yeah, but we usually think of heat as just a measure of temperature.
Right.
But it's also a form of energy, and it's essential to understanding how planes work.
I never really thought about heat as anything more than hot or cold.
It's more than that. Heat is all about the movement of molecules.
Okay.
The faster they jiggle around, the more heat energy they have.
So the more something jiggles, the hotter it is?
You got it.
And in aviation, you're saying heat is everywhere.
Everywhere.
Okay, so I get how heat is involved in the engine. Like, combustion makes heat, and that powers the plane.
Right. But it goes beyond just the engine.
Oh.
Think about friction between moving parts. That creates heat. Electrical resistance in wiring. That creates heat, too. And, of course, there's the heat released when you burn aviation fuel.
Right, which the handbook said 1 pound of
Mm-hmm.
has the potential energy of over 14 million foot-pounds of work.
That's an incredible amount of energy.
It really is.
Shows you the power of chemical energy.
But you're saying not all of that heat energy actually gets converted into useful work.
Yeah, that's where thermal efficiency comes in.
Thermal efficiency.
It's a ratio of usable power to the total potential power in a heat source.
So you're saying some of it gets wasted.
Unfortunately, yes.
How much?
Well, the handbook calculates that a typical piston engine in a small airplane has a thermal efficiency of about 27%.
So like over 70% is lost.
As heat to the surroundings, yeah.
Wow, that seems like a lot of wasted energy.
It is. There's a lot of research going into making engines more efficient.
That makes sense.
But anyway, if we're talking about heat being a big deal, we have to talk about how it moves around.
Like conduction, convection, and radiation. Remember those from school?
Exactly. The handbook does a great job of explaining those.
Okay, remind me how those work again.
So conduction is heat transfer through direct contact.
Like touching a hot pan handle.
Exactly. And different materials conduct heat at different rates.
Right, that's why a metal spoon gets hot faster than a wooden one.
Exactly. Then you have convection, which is heat transfer through fluid movement,
Fluids.
like air or water.
Ah, okay.
Think about a hot air balloon.
Okay.
The burner heats the air, making it less dense, so it rises, carrying the heat with it.
So it's like the heat is hitching a ride on the moving air.
Pretty much. And remember how the handbook mentioned using fins and airflow to cool electronic components?
Yeah.
That's convection in action too, increasing surface area to transfer heat to the air more efficiently.
Clever.
And lastly, you have radiation.
Radiation, that's the one that travels through space.
Exactly.
Yeah.
Heat transfer through electromagnetic waves.
So that's how we feel the heat from the sun.
Yep. Radiation doesn't need a medium like air or water.
It just zooms right through space.
At the speed of light, much faster than conduction or convection.
Okay, so we've got this invisible energy called heat moving around in all these different ways.
Uh-huh.
But how does all of this relate to airplanes?
Well, understanding heat transfer is critical for a lot of things.
Like what?
Designing efficient engines, cooling systems, and even making sure the materials can handle the heat generated during flight.
I never realized how much heat was involved in aviation.
It's a lot. And the handbook doesn't stop there.
There's more.
Oh yeah, it dives into another crucial element for flight, the atmosphere.
The atmosphere, right? It's more than just the air we breathe.
Right. It's got layers like the troposphere where most weather happens and the stratosphere, home to the ozone layer.
I vaguely remember those from science class.
But they play a big role in aviation.
Really? How?
The atmosphere provides the air that wings need to generate lift. It affects engine performance and even how pilots navigate.
So the atmosphere is like the playground for airplanes.
You could say that. And then there's air pressure, the force exerted by all that air above us.
That's what makes my ears pop during takeoff and landing.
Exactly. And as you go higher, the pressure decreases because there's less air above you.
Right. That's why it's harder to breathe at high altitude.
Exactly. The handbook describes the mercury barometer.
That thing with the mercury that rises and falls.
Yep. It measures atmospheric pressure, and standard atmospheric pressure at sea level is 14.7 psi.
Which is what our altimeters are calibrated to, right?
Exactly. So when you're cruising at 30,000 feet, the altimeter is actually measuring pressure and converting that to an altitude.
That's pretty clever.
It is a great example of physics in action.
Okay, so we've covered heat, the atmosphere, all these building blocks.
Yep, we're getting there.
Are we finally ready for lift? Like, how does it actually work?
We are. The handbook introduces the 4 forces acting on an airplane in flight.
4 forces.
Lift, weight, thrust, and drag.
Okay, break those down for
You're
me.
right. Lift is the upward force that opposes weight.
Which is the force of gravity pulling the plane down.
Right. Thrust is the forward force from the engines.
So that's what pushes the plane forward.
Exactly. And then you have drag, the resistance the plane encounters from the air.
So it's like the air trying to hold the plane back.
Kind of. And when all 4 of those forces are balanced, you have level flight.
Ah,
But if one force changes, the plane's flight path changes too.
like if the pilot increases thrust, the plane will accelerate.
Precisely. Pilots are constantly adjusting these forces to control the plane's altitude, speed, and direction.
Like a constant balancing act.
In a way, yes.
Okay, so that makes sense. But how does lift actually happen? Like, how does something as heavy as a plane actually stay up in the air?
That's the question that has fascinated people for centuries.
And the handbook has the answer.
Well, it delves into 2 key principles: Bernoulli's principle and Newton's third law of motion.
I've heard of Bernoulli's principle, but it always seemed really complicated.
It can be, but at its core, it says that faster moving air has lower pressure.
Okay.
And the shape of the wing, specifically the curved upper surface, is designed to make the air flowing over the top move faster than the air underneath.
So the wing is like shaping the airflow.
Exactly. That creates a pressure difference. Lower pressure on top, higher pressure underneath.
And that's what creates lift.
A big part of it, yes.
The handbook mentioned the Venturi tube, that thing that narrows in the middle.
Right.
It's like a mini wing, showing how the air speeds up and the pressure drops.
It's a great analogy. And then there's Newton's third law.
For every action, there's an equal and opposite reaction.
You got it. As the wing forces air downwards, the air pushes back up on the wing, also contributing to lift.
So it's a combination of Bernoulli's principle and Newton's third law that makes lift possible.
It's a beautiful interplay of physics principles.
This is amazing. And what about the angle of attack, the angle between the wing and the oncoming air?
That's crucial for controlling how much lift the wing generates.
So the steeper the angle, the more lift.
Generally, yes, but only up to a point.
What happens then?
If the angle gets too high, the airflow separates from the wing and you lose lift.
And that's called a stall, right?
Exactly. It can be dangerous, but pilots are trained to deal with it.
And the handbook explained how different wing designs and those things called flaps and slats can help prevent stalls.
It's all about controlling that airflow.
This is so cool. It's like this delicate dance of forces and airflow that keeps a plane up in the air.
It is. And the handbook goes into a lot more detail about the different types of flight controls.
Ailerons, rudders, elevators.
All these things working together to let the pilot maneuver the plane.
It's amazing how these concepts translate into the actual mechanics of flight.
It's a testament to human ingenuity and our understanding of physics.
This deep dive has been incredible. I feel like I've unlocked a whole new understanding of how the world works, and it all started with wanting to know how planes fly.
And as we continue to explore new frontiers in aviation, from space travel to who knows what else, it's physics that will guide us.
That's a great point. Physics is the key to unlocking so much potential.
It's what makes flight possible and will continue to shape the future of aviation.
This has been a fantastic journey, and I hope everyone listening is feeling inspired to keep exploring and learning.
There's always more to discover.
Thanks for joining us on this deep dive into the world of aviation physics. We'll see you next time.